Welcome back to The Quiet Explainer. Wherever you're listening from tonight, I'm glad you're here. This will be a long and unhurried exploration, so take a moment to settle in. There is nothing you need to solve immediately, nothing you need to memorize. You can simply listen. If you find value in these slow and structured explanations, subscribing helps support the channel. And I truly appreciate it. Now, for centuries, physics seemed complete. Objects moved in predictable ways. Forces caused motion. Energy flowed continuously. If you knew the position of something and you knew its speed, you could calculate its future. The universe appeared to be a clockwork machine, precise, stable, understandable. And for everyday life, it still is. Bridges stand. Planets orbit. Engines run. Classical physics works extraordinarily well. But near the end of the 19th century, small cracks began to appear. Light did not behave the way equations predicted. Atoms did not radiate energy the way they were supposed to. At first, these seemed like minor technical problems. They were not. They were signs that the foundation itself was incomplete. To resolve those cracks, physicists were forced to consider something radical. What if energy is not continuous? What if particles are not simply tiny solid objects? What if, at the smallest scales, nature does not follow the rules we built from everyday experience? Quantum physics did not emerge from imagination. It emerged from necessity. And over time, it revealed a picture of reality that is quieter, subtler, and more structured than most dramatic explanations suggest. Not mystical, not magical, but fundamentally different from the world we see. Tonight, we'll move slowly through the foundational ideas of quantum physics. We'll begin with the classical world, the one that works. Then we'll explore the problems that forced a new theory into existence. And step by step, we'll build an understanding of quantization, wave-particle duality, superposition, uncertainty, and measurement. No equations. No hype. Just structure. This is quantum physics explained slowly. Before we can understand quantum physics, we need to understand the world it disrupted. Because quantum theory did not appear in isolation. It emerged from a framework that already seemed complete. For centuries, the physical universe appeared orderly, predictable, deeply structured. Objects moved according to consistent rules. Forces caused motion. Motion followed precise mathematical laws. If you pushed a cart, it accelerated. If friction slowed it down, that slowing could be calculated. If you threw a ball, its arc through the air followed a clean and continuous curve. These principles were formalized in the 17th century by Isaac Newton. Newton's laws of motion described how objects respond to forces. His law of gravitation described how masses attract one another. With these tools, physicists could calculate the motion of planets, the tides of oceans, and the trajectories of projectiles. The universe behaved like a machine, a vast mechanical system composed of interacting parts. And machines, when properly understood, are predictable. If you know the starting conditions of a system, its position, its velocity, the forces acting upon it, you can calculate its future state. Not approximately, precisely. This idea is called determinism. Determinism means that the present completely determines the future. If an intelligence existed that knew the position and momentum of every particle in the universe is less than #0, 5# is greater than, it could, in principle, calculate the entire future of the cosmos. This was not fantasy. It was a logical extension of the equations. In classical physics, uncertainty does not belong to nature itself. It belongs to us. If we fail to predict something, it is because we lack complete information. The laws themselves remain exact. This worldview aligned with human intuition. We experience solid objects. We see continuous motion. We observe smooth changes in energy and speed. Energy, in the classical picture, is continuous. You can increase it gradually. You can decrease it gradually. There is no smallest required unit. If you heat an object, you can supply a little energy or a great deal. There is no conceptual gap between those amounts. Motion is continuous. Space is continuous. Time is continuous. Everything flows smoothly. By the 19th century, classical physics had achieved extraordinary success. It guided the design of bridges. It powered steam engines. It shaped the Industrial Revolution. Astronomers could predict eclipses decades in advance. Engineers could calculate stresses in steel. The framework worked. It was not fragile. It was robust. And because it worked so well, many physicists believed the foundation of physics was nearly complete. There were refinements to make, measurements to improve, but the structure itself seemed secure. The universe appeared understandable in mechanical terms. At the heart of this mechanical worldview was a simple assumption. Matter is made of small pieces, and those small pieces behave like even smaller machines. If you zoom in on reality, you should simply find smaller versions of the same rules. Tiny particles should have definite positions, definite velocities, definite trajectories through space. They should move along continuous paths. Just as planets orbit the Sun, electrons were imagined to orbit the nucleus of an atom. Smaller in scale, but conceptually similar. This extension downward seemed natural. Atoms had been proposed as the building blocks of matter. Later, electrons were discovered as components within atoms. The classical framework expanded to include them. Electrons were treated as tiny charged particles. And according to classical electromagnetism, charged particles that accelerate should radiate energy. An orbiting electron is constantly accelerating. Therefore, it should continuously emit energy. And if it emits energy, it should lose speed. If it loses speed, it should spiral inward and eventually collapse into the nucleus. But atoms do not collapse. Matter is stable. This was not a minor inconvenience. It was a direct contradiction. The classical model predicted instability. Reality displayed stability. This tension did not immediately overturn the framework, but it introduced doubt. And there were other signs of strain. When scientists studied heated objects, they measured the light those objects emitted. Classical equations predicted that at high frequencies, the energy emitted should become infinite. Infinite energy. This prediction was clearly wrong. Nature does not produce infinite radiation from ordinary heated matter. This discrepancy became known as the ultraviolet catastrophe. Again, it was not dramatic in tone. It was technical. But technical failures in fundamental equations matter. Because equations are not guesses. They are structural descriptions of reality. If they fail consistently, the structure beneath them must be reconsidered. By the late 19th century, physics stood in a strange position. It was immensely successful at large scales, yet increasingly unstable at small scales. The mechanical worldview had reached a boundary. Not because it was careless, not because it lacked rigor, but because nature, at very small scales, does not behave like a scaled-down machine. This realization did not arrive all at once. It emerged slowly, through experiments, through contradictions, through persistent failure to reconcile theory and observation. And yet, before moving forward, it is important to appreciate something. Classical physics was not wrong. It remains extraordinarily accurate at the scales we inhabit. The bridges still stand. The planets still orbit. the engineering calculations still work. Quantum physics does not erase classical physics. It refines it. It reveals that the classical world is a large-scale approximation of something deeper. But at the end of the 19th century, that deeper structure was not yet clear. All that was visible were cracks, small inconsistencies, uncomfortable predictions, unstable atoms. The mechanical universe, once so complete, was beginning to show limits. In the next section, we'll examine those cracks carefully. Because quantum physics did not begin with mystery. It began with failure. In the late 19th century, physics appeared nearly complete. The equations of motion were established. Electromagnetism had been unified. Thermodynamics described heat and energy. The structure seemed stable. And yet, beneath that stability, small inconsistencies were emerging. They did not arrive as dramatic revolutions. They arrived as technical problems. Subtle mismatches between theory and experiment. At first, many physicists assumed these discrepancies would eventually be resolved within the classical framework. After all, the framework had succeeded so many times before. But these new problems were different. They were not failures of measurement. They were failures of prediction. And they all pointed in the same direction. Something fundamental was missing. The problem of blackbody radiation. One of the most troubling issues arose from the study of heated objects. When you heat a piece of metal, it begins to glow. At lower temperatures, it glows red. As it becomes hotter, the glow shifts toward white. This glow is not random. It follows a measurable pattern of emitted radiation across different frequencies. Physicists wanted to calculate that pattern. Using classical electromagnetism and thermodynamics, they attempted to predict how much energy a heated object would emit at each frequency of light. At low frequencies, the predictions worked reasonably well. But at high frequencies, the equations produced an alarming result. They predicted that the energy emitted would increase without limit. Infinite energy at ultraviolet frequencies. This became known as the ultraviolet catastrophe. It was not simply a small error. It was a divergence to infinity. And nature clearly did not behave this way. Real heated objects emit a finite amount of radiation. The classical equations were structurally wrong. Planck's desperate assumption. In 1900, a physicist named Max Planck attempted to solve this problem. He was not trying to overturn classical physics. Is less than hashon, zero hash, is greater than. He was trying to patch it. To make the equations match experimental data, Planck introduced a mathematical assumption. He proposed that energy is not emitted continuously. Instead, it is emitted in discrete packets. These packets would later be called quanta. At first, Planck did not believe this reflected physical reality. He treated it as a computational trick. But the trick worked. The infinite divergence disappeared. The predicted radiation curve matched experiment precisely. A technical fix had succeeded, but it carried a profound implication. If energy is emitted in discrete packets, then energy is not continuous. That assumption alone contradicted centuries of classical thinking. And this was only the beginning. The photoelectric effect. Another problem soon intensified the crisis. When light shines on certain metals, electrons can be ejected from their surface. This phenomenon is called the photoelectric effect. Classically, light was understood as a wave. And in wave theory, energy is related to amplitude. Brighter light should deliver more energy. Therefore, classical reasoning predicted that increasing brightness should increase the energy of ejected electrons. But experiments showed something different. The energy of the ejected electrons did not depend on brightness. It depended only on frequency. Below a certain frequency threshold is less than #0. 5# is greater than. No electrons were emitted at all. No matter how bright the light was. This was deeply puzzling. According to classical wave theory, energy should accumulate gradually. Even low-frequency light, if bright enough, should eventually supply sufficient energy. But it did not. In 1905, Albert Einstein proposed an explanation. He suggested that light itself is quantized, not just emitted in packets, but fundamentally composed of discrete energy units. Each packet of light, later called a photon, carries energy proportional to its frequency. If the frequency is too low, no individual packet has enough energy to eject an electron. Brightness increases the number of packets, but it does not increase the energy per packet. This explanation matched experiment precisely, but it required something radical. Light, previously understood as a continuous wave, also behaves like a particle. Another crack in the classical picture. Atomic stability. Meanwhile, the structure of the atom posed its own challenge. The classical model treated electrons as orbiting charged particles. But as we noted earlier, accelerating charges radiate energy. An orbiting electron should lose energy continuously. It should spiral inward and collapse into the nucleus. Yet atoms are stable. Matter persists. This contradiction was unavoidable. The classical equations of electromagnetism demanded collapse. Nature refused. Something about the behavior of electrons within atoms was fundamentally different from classical expectations. Discrete spectral lines. There was another clue. When atoms emit light, they do not produce a continuous rainbow of colors. Instead, they emit specific, discrete frequencies. Sharp lines in a spectrum. Each element produces its own distinct pattern. Classical physics offered no clear reason why only certain frequencies should appear. If energy is continuous, emission should be continuous. But the data showed something quantized. Only specific energy differences were allowed. The atom seemed to operate with restrictions. Not every energy value was permitted. This was incompatible with classical continuity. A pattern emerges. By the early 20th century, these problems could no longer be dismissed as minor anomalies. Blackbody radiation suggested energy comes in packets. The photoelectric effect suggested light behaves like particles. Atomic stability contradicted classical electromagnetism. Spectral lines revealed discrete energy levels. Each problem alone might have been tolerable. Together, they formed a pattern. The pattern pointed toward discontinuity. At very small scales, nature does not appear continuous. Energy does not vary smoothly. Light does not behave purely as a wave, is less than Hession. 5 is greater than. Electrons do not orbit like miniature planets. The mechanical worldview was reaching its limits. Not because it failed at large scales, but because it assumed that small scales would behave similarly. That assumption was collapsing. The shift in perspective. It is important to notice something subtle here. None of these experiments were mystical. There were no philosophical arguments. There were measurements, data, clear experimental outcomes. Quantum theory did not begin with speculation about strange realities. It began with the refusal of equations to match observation. Physicists were not searching for weirdness. They were trying to preserve coherence. But preserving coherence required abandoning continuity. And that shift would reshape physics completely. In the next section, we will look closely at the first foundational idea that emerged from this crisis. The idea that energy itself is quantized, not as a mathematical trick, but as a fundamental property of nature. Because once energy is no longer continuous, the entire structure of classical intuition begins to change. Before the 20th century, most physicists believed something very simple about energy. They believed it flowed, like water from a faucet, like light from a lamp, like heat from a fire, continuous, smooth, infinitely divisible. If you wanted half as much energy, you simply had half. If you wanted a little less, you shaved off a little. There was no smallest piece, no minimum unit, no grain. Energy, they thought, was like a dimmer switch. You could slide it up, you could slide it down. Anywhere in between was allowed. And for centuries, this assumption worked beautifully until it didn't. Let's imagine something simple. A piece of metal, nothing exotic, just a solid chunk of iron. Now imagine heating it. At first, it warms quietly. Then it begins to glow faintly red. As it gets hotter, the glow shifts toward orange, then yellow, then white. This is something you've seen before. A stove coil, a blacksmith's forge, the filament in an old light bulb. Color changes with temperature. Simple, or so it seemed. Physicists wanted to describe exactly how much energy this glowing object emitted at each color, so they modeled it as something called a blackbody. Not literally black, but an ideal object that absorbs all incoming light and radiates energy perfectly. It was supposed to be an easy calculation, and at first, it seemed to be. Classical equations predicted how much energy would radiate at each frequency. Low frequencies, reasonable. Medium frequencies, still reasonable. But then, something strange happened. At very high frequencies toward ultraviolet, the equations predicted the energy would skyrocket, not just increase, explode. According to classical physics, a hot object should emit infinite energy at high frequencies. Infinite. That clearly wasn't happening. No stove was vaporizing the universe with ultraviolet light. This mismatch became known as the ultraviolet catastrophe. And it wasn't a small error. It was a fatal flaw. For years, physicists tried to patch the equations. Maybe a term was missing. Maybe an assumption was slightly off. But nothing worked. The problem wasn't the math. It was the underlying belief. Energy wasn't behaving continuously. Then, in 1900, a quiet and methodical physicist named Max Planck made a radical move. At first, he didn't even believe it himself. He proposed something strange. What if energy could not be emitted in arbitrary amounts? What if it came in small, indivisible packets, discrete chunks, tiny bundles, like coins instead of flowing water? Planck suggested that energy could only be exchanged in multiples of a tiny unit. That unit depended on frequency. The higher the frequency, the larger the energy packet. This constant of proportionality became known as Planck's constant. A very small number, incredibly small, so small that in everyday life we never notice its effects. But at microscopic scales, it changes everything. Think about stairs instead of a ramp. In classical physics, energy was a ramp. You could stand anywhere. In Planck's model, energy was a staircase. You could only stand on steps. No in between, no half step. This idea fixed the ultraviolet catastrophe instantly. When energy was quantized, the high-frequency explosion disappeared. The math now matched reality. The glowing iron behaved correctly. The catastrophe was gone. But this solution came with a cost. It shattered continuity, and continuity had been sacred. Planck himself initially treated quantization as a mathematical trick, a convenient fix, not a statement about reality. But others took it seriously. One of them was a young patent clerk in Switzerland. In 1905, Albert Einstein extended Planck's idea. He proposed that light itself was quantized, not just emitted in packets, but fundamentally made of packets, particles of light, later called photons. This explained something called the photoelectric effect. When light shines on certain metals, electrons are ejected. Classical theory predicted that brighter light would eject more energetic electrons, but experiments showed something different. Color mattered. Frequency mattered. There was a threshold. Below a certain frequency, no electrons were ejected, no matter how bright the light was. Above it, electrons were ejected instantly, as if light arrived in hits, impacts, discrete blows. Einstein proposed that light was made of quanta. Each photon carried energy proportional to its frequency. If the photon didn't have enough energy, it couldn't knock an electron loose. Brightness didn't matter. Only packet size did. This was deeply unsettling. Light had been understood as a wave for over a century. After the experiments of James Clerk Maxwell, electromagnetic waves were considered a triumph of classical theory. Now light was acting like a particle. Again, energy was no longer smooth. It was granular, at least sometimes. This wasn't just about light. Soon, physicists realized atoms themselves exhibited quantization. Electrons orbiting the nucleus did not possess arbitrary energies. They occupied specific levels, fixed amounts, like steps on a ladder. If an electron absorbed exactly the right quantum of energy, it could jump to a higher level. If it released energy, it fell to a lower one, but it could not exist between levels. No hovering halfway, no partial transitions, only jumps. These discrete energy levels explained atomic spectra. When atoms are heated, they emit light at specific colors, not a continuous rainbow, sharp lines, precise frequencies. Each line corresponds to a transition between energy levels. The staircase revealed itself in light. It was becoming impossible to ignore. Nature preferred steps, not ramps. This idea quantization feels small at first, just a tweak, but it is a deep shift in worldview. In classical thinking, continuity is fundamental. In quantum thinking, discreteness is fundamental. The world at small scales is not infinitely divisible. There is a smallest action, a smallest packet of energy exchange, governed by Planck's constant. Let's pause here. Take a slow breath. The air around you feels continuous, smooth, unbroken. But at microscopic levels, the energy moving through matter is quantized. Photons striking atoms, electrons jumping levels, discrete events, tiny stair steps everywhere. And yet, in your daily experience, everything feels fluid. Because Planck's constant is so small, the steps are microscopic. Billions of them blend into smoothness, like pixels on a screen. Up close, you see squares. From afar, you see an image. Quantization hides beneath perception. This principle will soon lead us somewhere even stranger, because once energy is quantized, motion behaves differently, stability behaves differently, possibility behaves differently. Atoms don't collapse into themselves because electrons cannot radiate arbitrary amounts of energy. They can only drop specific amounts. Quantization protects structure. It stabilizes matter. Without it, atoms would be unstable. Chemistry would fail. Stars would burn differently. Life might not emerge. A tiny constant, a tiny step size, holding the universe together. And all of this began with a mismatch in glowing metal, a mathematical catastrophe, a desperate proposal. Energy comes in packets. At first, it seemed like a patch. Then it became a pillar. Now, as we move forward, we will see that quantization is not an isolated quirk. It is part of a deeper pattern. Particles acting like waves. Waves acting like particles. Certainty dissolving into probability. Measurement changing outcomes. But for now, let's simply sit with this idea. Energy is not continuous. It is quantized, like footsteps instead of a slide, like notes instead of a continuous tone, like heartbeats instead of a hum. In the quiet fabric of reality, there are steps, invisible, tiny, relentless. And with that gentle realization, we are ready to step forward into wave-particle duality, where the staircase begins to blur. There was a time when the universe felt neatly organized. Waves were waves. Particles were particles. Water formed waves. Sand formed grains. Light, after the work of James Clerk Maxwell, was confidently placed in the wave category. Electric and magnetic fields oscillating through space. Elegant, continuous, predictable. Then energy became quantized. Then Albert Einstein suggested light came in packets, photons, tiny bursts, and suddenly something uncomfortable appeared. Light behaved like a wave and like a particle. At first, this seemed like a contradiction. Waves spread out. Particles are localized. Waves interfere. Particles collide. Waves pass through each other. Particles bounce. These are not small differences. They are fundamental. And yet, experiment after experiment refuse to cooperate with our categories. Let's return to something simple. Water. If you drop two pebbles into a still pond, ripples spread outward. Where the ripples meet, they interfere. Some places become higher crests. Some places cancel out. This is wave behavior. It's called interference. Now imagine firing tiny pellets at a wall with two narrow slits. If they are particles, you expect two clusters behind the slits. Two bands, like two bullet holes. Simple, direct. But when physicists performed this experiment with light, something astonishing happened. Instead of two bright bands, they saw many. A pattern of alternating bright and dark stripes. An interference pattern. Exactly what waves produce. This was known as the double-slit experiment, and it was decisive. Light behaves like a wave. Except when the light was turned down so low that photons passed one at a time, the pattern still built up, slowly, photon by photon. Each photon struck the screen as a localized dot, like a particle. But over time, the dots arranged themselves into an interference pattern, as if each photon had interfered with itself. Pause here. One particle going through two slits, producing an interference pattern. This is not intuitive. It is not mechanical. It is not classical. To make things even stranger, when detectors were placed at the slits to see which slit the photon went through, the interference pattern disappeared. Instead, two bands appeared. Particle behavior. Simply observing which path it took changed the outcome. Light refused to choose. Wave when unobserved. Particle when measured. This duality was not limited to light. In 1924, Louis de Broglie proposed something radical. If waves can behave like particles, maybe particles can behave like waves. He suggested that matter itself has a wavelength. Even electrons, even atoms, everything with momentum. At first, this sounded absurd. Electrons are tiny bits of matter. They have mass, charge. They are particles. But experiments soon confirmed it. When electrons were fired through a double slit, they produced interference patterns, just like light, just like waves. Matter behaved like a wave. Imagine holding a grain of sand. Now imagine that grain having a wavelength, spreading, interfering, oscillating. It feels almost poetic, almost mystical, but it is measurable, precise, mathematical. Wave-particle duality means that the entities we once called particles do not travel like tiny billiard balls. They are described by something called a wave function, a mathematical object that spreads through space. It does not describe a definite location. It describes probabilities, possibilities. When unmeasured, an electron behaves like a wave of potential. When measured, it appears as a particle, a localized event. This is not because the electron changes its mind. It is because our classical categories were incomplete. Waves and particles are not opposites. They are two aspects of a deeper quantum reality. To feel this gently, let's soften the mental picture. Imagine mist instead of stone. Imagine a cloud of possibility moving forward. When it meets a detector, it crystallizes at one point. But until then, it remains spread out. The wave is not a physical ripple in space like water. It is a ripple in probability, a pattern describing where something might be found. This subtle shift from certainty to probability begins here, with duality. And it unsettled the greatest minds of the time. Even Albert Einstein struggled with it. He accepted quantization. But the probabilistic nature of quantum mechanics troubled him deeply. He famously resisted the idea that nature was fundamentally uncertain. Yet the experiments kept confirming it, over and over. Light diffracts, electrons interfere, atoms form wave patterns. Wave-particle duality is not about confusion. It is about limitation. Our language was built for macroscopic objects, tables, rocks, oceans. At quantum scales, those intuitions dissolve. A photon is not a tiny marble, nor is it a smooth ripple. It is something that sometimes manifests as one and sometimes as the other, depending on the question we ask. This idea carries enormous consequences. If matter behaves like a wave, then electrons in atoms are not orbiting like planets. They are standing wave patterns, probability clouds, stable because only certain wave patterns fit. Quantization emerges naturally from wave behavior. Only certain wavelengths are allowed. Only certain energy levels exist. The staircase from section 3 now connects to the wave. Energy levels are discrete because waves must fit neatly. No half waves allowed. No mismatched oscillations. Take a breath. We began with glowing metal. We moved to packets of energy. Now we see that the very building blocks of matter are not solid points traveling fixed paths. They are spread out possibilities. And yet, when you touch a table, it feels solid, definite, certain. That solidity emerges from countless quantum wave functions interacting, a sea of probabilities giving rise to stability. Wave-particle duality invites humility. It tells us that reality at its smallest scales is not obligated to fit our mental categories. Instead of asking whether something is a wave or a particle, quantum physics answers gently, yes. In the quiet depths of the microscopic world, certainty softens. Objects blur into patterns. Events emerge from possibility. And as we continue forward, this duality will evolve into something even more delicate. Superposition, where not only behavior, but state itself becomes layered. For now, rest in this image, a single photon traveling through darkness, not as a point, not as a ripple, but as a quiet cloud of possibility. And when it meets the world, it chooses. Up until now, the strange ideas have been manageable. Energy comes in packets. Light behaves like a wave and a particle. Unusual, yes, but still tethered to something familiar. Now we step into a deeper shift, not about how things move, but about how they exist. In classical physics, an object has a state. A ball is here, not there. A coin is heads, not tails. A light is on or off, never both. This feels obvious. It feels unquestionable. Quantum mechanics asks us to loosen that certainty. Because when a particle is described by a wave function, a spread-out cloud of probability, it does not represent a single definite reality. It represents multiple possible realities at once. This is called superposition. Superposition means that a quantum system can exist in multiple states simultaneously. Not one or the other, but both, until measured. Let's approach this slowly. Imagine a coin resting under your hand. Without looking, you might not know whether it is heads or tails, but in reality, it is one or the other. Your ignorance does not change its state. Now imagine a quantum coin. Before you look, it is not secretly heads and not secretly tails. It is in a superposition of heads and tails. Both possibilities are real components of its state. This is not about lack of knowledge. It is about physical reality. To make this more concrete, physicists often describe something called spin. Electrons possess a property called spin. When measured along a direction, spin can be up or down. Only two outcomes. But before measurement, the electron's spin can be in a superposition of up and down, not undecided. Not hidden, but genuinely both components present in its wave function. When measured, the superposition resolves. One outcome appears, up or down. But prior to that measurement, the system is described as a blend of possibilities, a layered state. This layering is mathematical, precise, predictable in its probabilities, but conceptually unsettling. To feel it gently, imagine a musical chord. A single piano key produces one note, but a chord contains several notes at once. They coexist. They overlap. They form a richer sound. A quantum superposition is like a chord of possibilities, multiple states overlapping in the same system. And only when listened to, measured, does one note ring out clearly. One of the most famous illustrations of superposition came from Erwin Schrödinger. He proposed a thought experiment: a cat in a sealed box. Inside the box is a quantum mechanism that has a 50% chance of triggering a poison. If the quantum event occurs, the cat dies. If not, the cat lives. According to quantum mechanics, before opening the box, the quantum system is in superposition, triggered and not triggered. If the quantum system is entangled with the cat, then the cat would also be in a superposition, alive and dead, simultaneously. This was not meant to suggest that cats are literally smeared between life and death in our experience. It was meant to expose the strangeness of extending quantum rules to the macroscopic world. In daily life, we never see superpositions. Cats are alive, or they are not. So what changes between electrons and cats? Why do quantum possibilities seem to collapse into classical certainty? The answer begins with interaction. When a quantum system interacts with its environment, its delicate superposition spreads. It becomes entangled with countless particles. The layered possibilities interfere with one another, and stable classical outcomes emerge. This process is called decoherence. It does not require a conscious observer. It requires interaction, contact, connection. At tiny scales, superpositions are stable. At large scales, they dissolve almost instantly. The world we experience feels definite because superpositions rarely survive long enough to be noticed. But in carefully isolated systems, ultra-cold atoms, superconducting circuits, scientists can maintain superpositions. They can manipulate them, even use them. Quantum computers rely on superposition. Instead of classical bits that are 0 or 1, quantum bits, qubits, can exist in superpositions of 0 and 1, not as metaphor, but physically. This allows quantum computers to explore multiple computational paths simultaneously, like evaluating many possibilities at once. Superposition is not mystical. It is measurable, repeatable, harnessed in laboratories. And yet, its philosophical implications are profound, because it challenges the idea that reality is single-threaded before observation. Let's soften this idea again. Imagine a traveler at a crossroads. In classical physics, the traveler chooses a path, left or right. In quantum physics, the traveler explores both paths as a wave. The wave spreads, interferes, overlaps. Only when arriving at a destination when measured does a single path become definite. Before that, the system contains multiple potential histories. This is not easy for the mind to hold, and it is not meant to be. Quantum mechanics does not ask us to feel comfortable. It asks us to follow the mathematics, and the mathematics works with astonishing precision. Every experiment so far agrees. Superposition is real, at least at microscopic scales. Take a slow breath here. Notice how your mind wants to reduce it, to simplify it, to say, surely it must secretly be one or the other. That instinct is classical thinking. Quantum theory gently resists it. A system is described fully by its wave function, and that wave function can contain multiple components simultaneously. When measured, one component manifests, but the probabilities of those outcomes depend on how the components interfere. Superposition leads directly to interference, and interference leads directly to observable patterns. This is why the double-slit experiment works. Each particle passes through both slits as a superposition. The components interfere, and the pattern emerges. If you measure which slit it went through, you destroy the superposition. No interference, just particles. Superposition is fragile. Measurement is decisive. In the quiet interior of atoms, countless superpositions flicker. Electrons existing in blended states, photons in overlapping paths, possibilities layered like transparent sheets. And yet, here you are, sitting in a room, feeling definite, solid, certain. That certainty emerges from immense complexity, from decoherence washing out fragile layers of possibility, from interaction stabilizing outcomes. Quantum mechanics does not erase reality. It reshapes our understanding of when reality becomes definite. Before measurement, there is a field of potential. After measurement, there is an outcome. In that gentle transition lies one of the deepest mysteries in physics. Why does measurement select one possibility? What determines the outcome? Is it randomness? Is it hidden structure? Is it branching universes? Different interpretations offer different answers, but all agree on the mathematics. Superposition exists. For now, let the philosophical debates rest. Let the image remain simple. A system containing multiple possible states, coexisting, overlapping, until interaction draws one into focus. In the soft darkness before observation, reality is not singular. It is layered. And in our next section, we will explore something that grows naturally from this idea: the limits of certainty itself, the uncertainty principle. In classical physics, the universe is precise. If you know the position of a planet and its velocity, you can predict its future. If you know the starting conditions perfectly, you can calculate everything that follows. This worldview reached its peak with Isaac Newton. Motion was deterministic. Cause led to effect. The future unfolded from the present like clockwork. There was, in principle, no limit to knowledge, only limits to our patience or instruments. Then, quantum mechanics arrived, and with it, something far more radical, than wave-particle duality, a limit not of technology, but of nature. In 1927, Werner Heisenberg introduced what we now call the uncertainty principle. It is often summarized simply: you cannot know both the exact position and exact momentum of a particle at the same time. The more precisely you know one, the less precisely you can know the other. This is not because measuring one disturbs the other. That explanation is common, but incomplete. The deeper reason lies in the wave nature of matter. Let's approach this gently. Earlier, we described particles as wave functions, not points, but spread out probability waves. Now imagine a perfectly pure wave, a single smooth oscillation extending infinitely in space. It has a perfectly defined wavelength, which means it has a perfectly defined momentum. But where is it? Everywhere. It stretches infinitely. Its position is completely uncertain. Now imagine squeezing that wave, localizing it into a small region. To do that, you must combine many different wavelengths, many different momenta. They interfere in such a way that the wave becomes localized. The more tightly you localize it, the more wavelengths you must combine, and the wider the range of momenta becomes. This is not a flaw. It is mathematics. It emerges from the structure of waves themselves. A sharp spike in position requires a spread in momentum. A sharp definition of momentum requires a spread in position. The uncertainty principle is not about disturbance. It is about the nature of waves. And since matter behaves like waves, matter inherits this limit. Formally, the principle states, the uncertainty in position multiplied by the uncertainty in momentum must be greater than or equal to a tiny constant. That constant contains Planck's constant, the same tiny number that introduced quantization. Again, that small constant quietly governs the microscopic world. Let's feel this intuitively. Imagine trying to locate a single electron precisely. To see something small, you need light. To see something very small, you need very short wavelength light, high-frequency light. But high-frequency light carries high energy, and high-energy photons transfer significant momentum when they collide. So, the very act of pinpointing the electron's position injects uncertainty into its motion. This is the intuitive explanation. But remember, even without measurement, the uncertainty exists. It is built into the wave function. The electron does not secretly have both exact position and exact momentum. Those quantities are not simultaneously well defined. In classical physics, we imagine a tiny particle traveling along a precise path. In quantum physics, that precise path does not exist. Instead, there is a spread of possibilities, a probability distribution. This changes how we think about prediction. We no longer predict exact outcomes. We predict probabilities, distributions, likelihoods, and yet quantum mechanics is astonishingly accurate. It predicts those probabilities with incredible precision. Uncertainty does not mean chaos. It means limits on simultaneous precision. Take a slow breath here. The idea can feel unsettling. We are used to thinking that things exist in definite states, whether or not we measure them. Quantum mechanics suggests something subtler. Certain pairs of properties do not have definite simultaneous values, not hidden, not waiting, undefined. Position and momentum are one pair. There are others, energy and time, different components of spin. The deeper mathematics reveals that these quantities correspond to operators that do not commute. Their order matters, and from that mathematical structure, uncertainty emerges inevitably. It is not philosophical, it is structural. This principle explains why electrons do not spiral into the nucleus. If an electron were confined to an extremely tiny space near the nucleus, its position uncertainty would be very small, which means its momentum uncertainty would be enormous. It would possess extremely high kinetic energy. Nature finds a balance. Electrons occupy orbitals standing wave patterns that minimize energy while respecting uncertainty. So, uncertainty is not merely a limitation, it is stabilizing. It shapes atomic structure. It shapes chemistry. It shapes matter itself. Without the uncertainty principle, atoms would collapse. Stars would behave differently. The periodic table would not exist as we know it. A fundamental fuzziness, holding reality in place. Now consider what this means for determinism. In Newton's universe, if you knew everything exactly, you could predict everything. In Heisenberg's universe, exact knowledge is impossible, not because we are ignorant, but because the world does not supply that information. This does not destroy causality. Quantum systems evolve deterministically according to equations. The wave function evolves smoothly, predictably. But when measured, outcomes occur probabilistically. The evolution is precise. The results are statistical. Einstein struggled with this. He famously resisted the idea that probability lay at the heart of nature. He suspected hidden variables, deeper layers, but experiments testing these ideas have repeatedly supported quantum predictions. Uncertainty is not a placeholder. It is fundamental. And yet, it is gentle. At large scales, uncertainty becomes negligible. Planck's constant is so small that macroscopic objects appear precise. A baseball's position and momentum can be known extremely accurately. The uncertainty exists, but it is unimaginably tiny relative to the scale. So, classical certainty emerges as an approximation, a limit case. Quantum mechanics does not erase the classical world. It underlies it. Let the idea settle softly. The universe is not infinitely sharp. It is subtly blurred. At the deepest level, reality has a built-in softness, a minimal grain of indeterminacy. This does not make the world fragile. It makes it textured, rich, dynamic. In the next section, we will explore something that naturally follows from uncertainty and superposition: measurement. And the question that lingers quietly beneath everything we've discussed: what does it mean to observe? For now, rest with this. There are limits to what can be known simultaneously, not imposed by us, but woven into the structure of existence. And within those limits, the universe continues its quiet unfolding. So far, we have moved gently through a series of shifts. Energy comes in packets. Light behaves like a wave and a particle. Particles exist in superpositions. Certainty has limits. Now we arrive at a question that sits quietly beneath all of them. When does possibility become fact? In quantum mechanics, before measurement, a system is described by a wave function, a spread of possibilities, multiple potential outcomes. After measurement, only one outcome is observed: one position, one spin, one result. What happened in between? This transition from superposition to a single outcome is called wave function collapse, and it is one of the deepest mysteries in physics. Let's approach it slowly. Imagine again the double-slit experiment. A particle approaches two slits. If unobserved, it behaves like a wave. It passes through both slits in superposition. An interference pattern forms. But if we place a detector to determine which slit it passes through, the interference disappears. The particle behaves classically. It chooses one path. The mere act of measurement changes the outcome. But what counts as measurement? Is it a conscious observer, a camera, an interaction with any particle? In modern physics, measurement does not require a human mind. It requires interaction. When a quantum system becomes entangled with another system, such as a detector, information about its state spreads into the environment. This process is called decoherence. We touched on it earlier. Now we look more closely. A quantum system in superposition is delicate. Its different components can interfere with one another. That interference is what produces uniquely quantum effects. But when the system interacts with its environment, air molecules, photons, surrounding atoms, the components of the superposition become correlated with countless external degrees of freedom. The interference patterns effectively disappear. The system appears to choose a definite outcome, but technically, the total system particle plus environment is still described by a larger wave function. This is subtle. Nothing magical happens. No sudden physical explosion. Instead, coherence, the delicate alignment of phases between components, is lost. To understand this intuitively, imagine two perfectly synchronized dancers. As long as they remain synchronized, their movements create a clear pattern. If one dancer becomes entangled with a crowd of other dancers, losing synchronization, the clear pattern dissolves. Decoherence explains why we do not observe macroscopic superpositions, why chairs are not simultaneously here and there, why cats are not visibly alive and dead. The environment constantly interacts with large systems. Superpositions become entangled and effectively classical almost instantly. But decoherence alone does not fully solve the mystery. It explains why interference disappears. It explains why outcomes look definite, but it does not explain why one specific outcome occurs rather than another. When you measure an electron's spin, you get up or down. Quantum mechanics gives you the probabilities, but it does not specify which individual result you will obtain. This randomness appears fundamental, not due to hidden ignorance, not due to incomplete knowledge, fundamental. This troubled many physicists, including Albert Einstein. He resisted the idea that nature is intrinsically probabilistic. He suspected deeper variables, hidden layers determining outcomes. But decades of experiments, particularly those testing Bell's inequalities, have strongly supported quantum predictions. Local hidden variable theories do not match observed correlations. Nature appears genuinely non-classical. Measurement, then, is not just passive observation. It is an interaction that transforms possibilities into experience. Some interpretations of quantum mechanics attempt to soften this transition. The Copenhagen interpretation suggests that the wave function represents knowledge. Collapse represents an update in information. Other interpretations, like the many worlds interpretation proposed by Hugh Everett, suggest that collapse never truly occurs. Instead, all outcomes happen. The universe branches. Each possibility becomes real in a different branch. In that view, measurement is not selection. It is splitting. There are other interpretations still. Objective collapse theories. Pilot wave theories inspired by David Bohm. Each preserves the mathematics. Each differs in ontology in what they claim truly exists. What is remarkable is this. Despite disagreement about interpretation, the predictive framework works flawlessly. Experiments match the equations again and again. So, what does measurement mean for us? It means that the act of interaction is fundamental. Reality at small scales is relational. Properties are not fully definite in isolation. They become definite through interaction. This does not imply that consciousness creates reality. It implies that physical systems influence one another. Information spreads. Correlations form. Outcomes stabilize. Think of measurement as crystallization. Before interaction, there is a fluid field of potential. After interaction, one structure solidifies. And yet, the underlying quantum evolution continues, always evolving, always unfolding. Take a slow breath here. Measurement is where quantum theory feels most philosophical. It brushes against questions of existence, observation, and reality. But at its core, it is physical. It is about interaction, entanglement, information. Entanglement deserves a brief pause. When two particles interact and become entangled, their states become linked, not classically correlated, quantum correlated. Measuring one immediately determines properties of the other, even if separated by vast distances. This phenomenon deeply unsettled Einstein, who referred to it as spooky action at a distance. Yet, experiments have repeatedly confirmed it. Entanglement means that measurement does not merely reveal properties, it establishes relationships. The universe at quantum scales is less like isolated objects and more like a web of interactions. When you measure a system, you become part of that web, your measuring device, your laboratory, the environment, all entangled. The clean boundary between observer and observed dissolves. There is only interaction. And from interaction, definite outcomes emerge. But the deeper question remains open. Why this outcome? Why now? Why not another? Quantum theory answers with probability. Nothing more, nothing less. This probabilistic nature is not chaotic. It follows precise statistical laws. Over many measurements, patterns emerge. Reliable, repeatable, stable. But each individual event retains unpredictability. In this way, quantum mechanics blends determinism and randomness. The wave function evolves deterministically. Measurement outcomes occur probabilistically. The universe is neither rigid clockwork nor wild chaos. It is structured probability. As we prepare to move into our final section, let this idea settle softly. Before interaction, there is superposition. After interaction, there is outcome. Between them lies the quiet mystery of measurement. Possibility becomes fact. Potential becomes experience. And from these countless tiny acts of crystallization, the classical world emerges. Solid, stable, certain. Next, we will step back and ask the final question. Why does all of this matter? We began in certainty, a solid world, predictable motion, a clockwork universe. Then, piece by piece, that certainty softened. Energy came in packets. Light behaved like both wave and particle. Matter spread into superpositions. Knowledge found its limits. Measurement reshaped possibility into fact. It might be tempting to ask, why does any of this matter? If tables remain solid, if the sky remains blue, if the world still turns beneath our feet, why concern ourselves with such strange foundations? The first answer is practical. Quantum mechanics is not philosophy alone, it is technology. Every transistor in your phone operates using quantum principles. The understanding of semiconductors, how electrons move through materials, depends on quantized energy levels and wave behavior. Without quantum mechanics, modern electronics would not exist. Lasers rely on stimulated emission, a quantum process predicted by Albert Einstein. Magnetic resonance imaging (MRI) machines depend on quantum spin. Solar panels rely on the photoelectric effect. The strange rules of the microscopic world quietly power the macroscopic world you live in. Even the stability of matter itself depends on quantum principles. Atoms do not collapse because of the uncertainty principle. Chemistry works because electrons occupy discrete energy levels. The periodic table exists because wave functions form structured patterns. So in one sense, quantum mechanics matters because it works. It describes reality with extraordinary accuracy. But there is a deeper reason, a quieter reason. Quantum mechanics matters because it reshapes how we understand reality. For centuries, we imagined the universe as composed of tiny solid objects, definite, self-contained, independent. Quantum theory dissolves that image. At the deepest level, reality is not made of tiny billiard balls. It is made of relationships, probabilities, interactions. Particles are not simply things. They are excitations in underlying fields, patterns of energy, temporary ripples in something deeper. In modern quantum field theory, even the concept of a particle becomes secondary. Fields are fundamental. Particles emerge from them. This shift is profound. The world is less like a collection of objects and more like a dynamic process. Even emptiness is not truly empty. The vacuum contains fluctuations, virtual particles appearing and vanishing, a restless background hum. The quiet void is not silent after all. Quantum mechanics also forces us to reconsider certainty. In daily life, we crave definite answers, yes or no, true or false, on or off. Quantum reality lives comfortably with probability, not as ignorance, but as structure. This does not mean anything can happen. It means outcomes are distributed, weighted, ordered by precise laws. The universe is not random chaos. It is statistical elegance. There is humility in this, a recognition that complete knowledge, in the classical sense, may not exist. And yet, Within those limits, extraordinary understanding is possible. Quantum predictions match experiments to astonishing decimal places. The theory is subtle, but it is not vague. Quantum mechanics also matters because it connects to the largest scales. Without quantum fluctuations in the early universe, structure might not have formed. Tiny variations, born from quantum uncertainty, were stretched during cosmic inflation. Those variations became galaxies, stars, planets. In a sense, the large-scale structure of the cosmos traces back to microscopic quantum fluctuations. The strange rules governing electrons also helped shape galaxies. And then there is entanglement, perhaps the most beautiful implication of all. Entanglement tells us that systems can become deeply correlated, so deeply that describing them independently becomes impossible. Two particles, once entangled, share a joint state, even when separated by vast distances. This is not faster-than-light communication. It does not break relativity, but it reveals that separateness is not always fundamental. At quantum scales, the universe behaves less like isolated fragments and more like a connected web. This challenges our intuition of independence. The classical idea that objects possess intrinsic properties regardless of context. Quantum mechanics suggests properties arise in interaction. This is subtle and easily overstated, but it invites reflection. We are not detached observers of a rigid machine. We are participants in a web of interactions. Even the act of measurement entwines systems together. Observer and observed form a temporary whole. There is something quietly poetic about that. But let us remain grounded. Quantum mechanics does not imply mysticism. It does not imply consciousness shapes reality. It does not erase objectivity. It simply reveals that reality at small scales operates differently than our instincts expect. And that difference matters. It matters for technology. It matters for cosmology. It matters for philosophy. It reminds us that human intuition evolved at a certain scale, a scale of rocks and trees, not electrons and photons. When we step outside that scale, we must rely on mathematics more than metaphor. And yet, even without equations, we can appreciate the shift. The universe is not a rigid clock. It is a dynamic unfolding of structured possibilities. Solid matter emerges from probability waves. Certainty emerges from decoherence. Classical reality emerges from quantum foundations. The world you experience is not separate from quantum mechanics. It is built from it. Every atom in your body obeys these rules. Every neuron firing in your brain, every breath. The solidity you feel is an emergent stability. from countless quantum interactions. There is something deeply humbling in that. We began this journey seeking to explain the microscopic world, but along the way, it explained something about us. Our need for certainty, our discomfort with ambiguity, our instinct for clear categories. Quantum mechanics invites a gentler posture, a willingness to accept layered reality, a comfort with probability. Not everything resolves into sharp lines. Some truths exist as distributions. And yet, the universe remains astonishingly comprehensible. That may be the most remarkable fact of all. From glowing metal to superposition, from wave-particle duality to entanglement, a coherent mathematical framework describes it all. It may not be intuitive, but it is beautiful. So why does quantum physics matter? Because it reveals that beneath the apparent solidity of the world lies something far more delicate. A tapestry of probabilities, a web of interactions, a quiet sea of potential. And from that sea, stars ignite, planets form, life emerges, thought arises. Even this moment, you listening now, is supported by quantum structure. The photons from your screen, the electrons in your device, the atoms in your ears, all dancing according to these strange, elegant rules. And yet, here you are, calm, resting, certain enough to breathe. Quantum mechanics does not remove meaning from the world. It deepens it. It tells us that certainty is emergent, that connection is fundamental, that possibility precedes form, and that even in uncertainty, there is order. So as we close this quiet exploration, let the strangeness settle softly. The universe is not less real than you imagined. It is more subtle. Not less stable, more intricate. Not less understandable, but more profound. Beneath the solid floor, beneath the steady stars, beneath even your own thoughts, there is a quiet field of possibility. And from it, moment by moment, reality gently unfolds. We've traveled far tonight, from glowing metal to probability waves, from solid certainty to layered possibility. And now there is nowhere left to go, only a quiet return. Take a slow breath. Let the equations fade. Let the terminology soften. You do not need to hold all of it. You do not need to understand every layer. Just the feeling of it is enough. Once, the universe seemed like clockwork, precise, predictable, certain. Then we looked closer, and certainty dissolved into quantized packets of energy. Particles became waves. Waves became probabilities. Possibilities overlapped in superposition. Position blurred with momentum. Knowledge found its limit. And measurement, that quiet act of interaction, turned potential into experience. But here, now, in this moment, the floor still feels solid. Your breath still rises and falls. The room around you remains steady. Quantum mechanics did not remove the world. It revealed its foundation. Beneath the solid surface is motion. Beneath motion is pattern. Beneath pattern is probability. And beneath probability, a quiet field of possibility. Every object around you is made of atoms. Every atom is mostly empty space. Every electron exists as a spread of likelihood. And yet the world holds together, stable, calm, coherent. There is something comforting in that. Reality is not rigid, it is resilient. It does not demand perfect certainty. It operates beautifully within gentle uncertainty. Even you, your thoughts, your awareness, your listening are supported by quantum structure. Neurons firing, ions shifting, electrons moving between energy levels, all following the same quiet rules that govern distant stars. In the early universe, tiny quantum fluctuations were stretched across cosmic scales. Those fluctuations became galaxies, stars, planets, and eventually, you. There is something deeply peaceful about that continuity. The smallest scales and the largest scales woven together. The uncertainty of an electron echoing in the structure of the cosmos. And yet, here you are, resting, breathing, listening. The mind often wants sharp answers, clear edges, binary certainty. Quantum mechanics offers something softer, not chaos, not confusion, but layered truth. It tells us that reality is not fragile because it is probabilistic. It is dynamic, not fixed stone, but flowing structure. and flowing things can be stable. A river is not rigid, yet it persists. The universe is not a static machine. It is a continual unfolding, moment by moment, interaction by interaction, possibility becoming form. Now, let all of that complexity settle. You do not need to trace wave functions. You do not need to picture superpositions. Simply feel the quiet idea. Beneath everything solid is gentle motion. Beneath certainty is structured uncertainty. Beneath separation is connection. The atoms in your body were forged in ancient stars. Those stars formed from quantum seeds billions of years ago. The same rules that guide an electron's dance guide the fusion in the sun. And that sunlight, traveling across space, is now reflected softly in your room. The universe is not distant from you. You are an expression of it. A temporary, beautiful arrangement of probability and pattern. And in this moment, all of it is steady enough for you to rest. Let the ideas drift like fog. Let the language fade. You do not need to solve the universe tonight. It is enough to know that beneath the surface of things, there is quiet elegance. Energy in packets, waves in matter, uncertainty as structure, measurement as crystallization. All of it unfolding without urgency. And now, so can you. Feel the weight of the room. Feel the steady rhythm of your breathing. The world remains here, stable, gentle. Quantum and classical, possibility and form. Not in conflict, but layered. If your mind wanders, let it wander softly. If sleep approaches, let it approach gently. The universe will continue its quiet dance, whether you are awake to observe it or not. And beneath it all, a field of possibility, humming quietly into form. Rest there,